Yeah, good morning students. Today we are going to discuss IIT-JEE NEET Foundation. The topic is mechanics. In the mechanics there are conservation of energy. Law of conservation of energy. Energy neither created nor destroyed. It transforms one form of energy to another form. So energy remains constant. If energy disappears in one form, then reappears in another form. For example, you take the sun energy, photosynthesis, it producing carbohydrates. That carbohydrates, trees are growing and later it be converted into coal. Coal will be converted into heat and other energies, light energies, and that heat energy will be converted to electrical energy. So it is only conversion process of 100% utilization of energy. It is something one form to another form. Energy is defined as the capacity to do work. The energy is capacity to do work. In the physics there is a law of conservation of momentum, law of conservation of energy, law of conservation of angular momentum. In the law of conservation of energy, one energy is equal to mc square. This is Einstein's energy, Einstein's mass energy equivalence equation. Einstein's mass energy equivalence equation E is equal to mc square. So where E is the energy produced, m is the mass defect which is there in the nuclear reactions. In the nuclear reactions, whenever nuclear splits into two different nuclei, so in that process when neutron is bombarded with the high energy, so with there is a neutron if it is bombarded with the nucleus defragments, means it splits into two different nuclei and another 3 neutrons will be released. So that another 3 neutrons, and there is enormous amount of energy released. That energy is equal to E. M is, there is, reactants and products, there is a certain mass defect will be there. That mass defect is converted into energy. Here C is the velocity of light in the vacuum. So 3 into 10 to the power of 8 meters per second, C value, the velocity of light in the vacuum. So this is Einstein's mass energy equivalence. Einstein's mass energy and mass mutually convertible each other. Energy and mass mutually convertible each other. That equation is E is equal to mc square, Einstein's equation. And another mechanical problem solving, work energy principles and fundamental principles. In the law of conservation of energy, the fundamental principle if you take, in the fundamental principles, like conservation of energy in the fundamental principle, this conservation of energy is used in many laws. Something like in the fluids, in the fluid mechanics, law of conservation of energy, fluids we are going to use, and the Bernoulli's equation. In the Bernoulli's equation also, Bernoulli's equation in the fluids, there is conservation of energy will be used. Something like Bernoulli's equation is, Bernoulli's effect like pressure energy and potential energy, then kinetic energy. This potential energy, kinetic energy and pressure energy all remains constant. Energy per unit volume should be taken as a constant. P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. Bernoulli's equation, just it is going to explain. For example, if there is a pipeline is there, here if you observe, the equation of continuity is also explained here. There is a pressure at this place, this is a pipeline, the area of cross sections are changing. Here area of cross section is bigger, here area of cross section is smaller, area of cross section is bigger. Let us take at this point the pressure is P1, the speed of the fluid particles is V1, At this point pressure is P2, the speed of the particles, speed of the water, okay, you can take it as V2. So according to the Bernoulli's equation, see that the equation of continuity is also can be used here. A1 V1 equal to A2 V2. A1 V1 equal to A2 V2. A1 is the area of cross section at this point and V1 is the speed. A2 is the area of cross section at this point and V2 is the speed. So equation of continuity states that it is the area into speed remains constant. Of course we will have more discussion in that, but here according to the law of conservation of energy, if you observe here, if area is greater and speed will be lower, so that all can be taken, and pressure also will be changed. Pressure also accordingly will be changed. According to the law of conservation of energy, the sum of pressure energy, kinetic energy and potential energy remains constant. That only says that P1 plus half rho V1 square. Rho is the density of the water, density. V1 is the speed at that point, and see, G is the acceleration due to gravity. H1 is height, datum, how much, okay, so from the base, how much height the pipe is there, or some flow where it is going to be there. This is about the Bernoulli's equation. This also follows law of conservation of energy. So next, coming to the another important law of conservation of energy in the electricity. In the electricity we use voltage law. See, in the voltage law, this law of conservation of energy again we are going to use. That is, energy remains constant. In the voltage law, what is voltage law? Voltage, Kirchhoff's voltage law. The algebraic sum of all voltages in a given loop is equal to 0. Algebraic sum of all voltages in a given loop is equal to 0. It means that if there is a circuit is there, the circuit, it consists of, there is a resistor and R1 and R2 are the resistors and VB is the potential difference. If you observe carefully, see the voltage law says that the voltage across any loop remains constant. Voltage across, the net voltage drop around the any closed loop must be 0. See, net voltage drop will be remains 0. That what she is explaining. Voltage law also it explains that law of conservation of energy. Energy will be constant. This is also combining all resistor. Here there is certain voltage will be there across R1. If you observe this example, voltage is here 12 volts and the current passes through this 8 amperes, and this current is split into two currents, 2 amperes and 6 amperes. The resistance here 6 ohms and 2 ohms. Now if you observe carefully, 6 into 12 is 12, so this is also 12. So 12 minus 12 it becomes 0. So this loop, the first loop, if you observe, the first loop it is going to be the, see, if you observe carefully, in this loop the voltage law if you apply, so 12 volt minus, okay, so voltage across this resistance is current into resistance. Current is 2 amperes and so resistance is 6 ohms. It means that 2 into 6, 12. 12 minus 12 it becomes 0. See, algebraic sum of all voltages in a loop is equal to 0. In this loop, as similarly if you take this loop, so that loop also, here the current is 6 amperes and resistance is 2. 12 minus again this also, see, 6 ohms and 12 amperes. 12 minus 12, this loop also will be 0. So it means, okay, algebraic sum of all voltages across a loop is equal to 0. That point you have to understand. In the series connection is also, if the same circuit, if resistors are there, in the series connection also, across the voltages if you observe, see here 12 volt is there, here 12 volt is there, the voltage drop across the, in the series connection, see the current passes through the circuit is 1.5 amperes. Because effective resistance will be changed. Effective resistance is how much? Here 6 ohms and 12 ohms. So 12, so it means that 6 plus 2 is 8. 12 by 8 it becomes 1.5. 1.5 amperes is the total current. So the total current, see will be same across the circuit. This 1.5 amperes will be there across R1 and 1.5 amperes will be there across R2 also. See 1.5 into 6, that becomes 9 volt, means across R1 the voltage drop is, okay, 9 volt drop will be there. Across R2 1.5 into 2, 3 volts, total is 12 volts, 9 plus 3, 12 volts. See, this is the series connection. In the series connection also, if you observe, voltage across this is 9, this is plus 3, 9 plus 3, 12 minus 12, it again 0. So the voltages in a loop, the sum of voltage, algebraic sum of all voltages in a loop is equal to 0. This voltage law follows law of conservation of energy. Voltage is nothing but amount of work done to carry the charge. It is work only. Voltage is amount of work done to carry the charge. The work is equal to energy. That's why it is also followed. See, voltage law, that Kirchhoff's voltage law follows law of conservation of energy. Kirchhoff's current law follows law of conservation of charge. But Kirchhoff's voltage law follows law of conservation of energy. So it means, see, law of conservation of energy used in the electricity, law of conservation of energy is used in fluid mechanics also. Fluid mechanics, Bernoulli's equation. In electricity, Kirchhoff's voltage law. See, coming to the next, see, law of conservation of energy is also used in the heat lesson. In the heat lesson, the first law of thermodynamics. The first law of thermodynamics states that, see, the change in internal energy is equal to the, see, the heat supplied minus work done. This is also going to follow law of conservation of energy. See, the first law of thermodynamics states that the amount of internal energy is equal to, the change in internal energy of the system is equal to the heat supplied to the system minus the work done by the system. The heat supplied to the system by work done by the system. So that's only the same formula, delta U is equal to Q minus W. Delta U is equal to Q minus W. So that means it is total heat minus total work done is nothing but change in internal energy. So that is what the first law of thermodynamics. See, in the first law of thermodynamics, it also going to follow law of conservation of energy. This is, will explain in the heat lesson more clearly. So it means, see, law of conservation of energy is used in the, see, physics. There are 3 different chapters. In one chapter, that is fluid mechanics. In the fluid mechanics, Bernoulli's equation. In another chapter, electricity, it is used in Kirchhoff's voltage law. Another chapter, heat. There, in the first law of thermodynamics, also law of conservation of energy is used. So, law of conservation of energy is the very, very important principle in the physics. It's a very, very important principle where it is in all different chapters you observe the laws are there. See, the mechanics problem solving. In the law of conservation of energy, the mechanics problem solving, we will use work energy equation. See, the amount of work done is equal to the change in kinetic energy. That, okay, stopping of an automobile, work energy principle is used. Object is falling from the rest. It is going to follow law of conservation of energy. See, when object is falling from the rest, whenever object is falling, so at 3 different points, if you observe carefully, 3 different points, different, see, let us take, if the object is there, if it is falling from certain height, if it is falling from certain height, so what is the, see, energy which is going to be there? If you observe carefully, here object is falling from the certain height. Here the kinetic energy at this point, if you observe, the kinetic energy will be 0, but potential energy is going to be there. Here kinetic energy will be 0, potential energy will be there, mgh. Mgh will be there because it is there at certain height. If it is falling to the ground, there is a kinetic energy will be exist. Kinetic energy is equal to half mv square, but potential energy will be 0. It means here kinetic energy is 0. Kinetic energy is 0 converted into kinetic energy. So it means there is a potential energy exists at the height which is converted into kinetic energy. So that's what, if you take one example, let us take, see the body is falling from certain height. The points, if you take here A and this is B and this is C. So at the point A, the potential energy, if you calculate, this A is there from the ground at a height h. A is there at a ground from the height h. See, let us take here the potential energy at A. The potential energy at A is equal to mgh. But kinetic energy at A is equal to 0. Kinetic energy at A is equal to 0. The point B is there from the ground at a height x. The point B is there from the ground at a height x. So then potential energy at B is equal to, the potential energy at B is equal to mgx, because at a height x it is there. But what is the kinetic energy? See, kinetic energy at B is equal to, if you try to find out the value of velocity at B. So value of velocity at B, actually v square minus u square is equal to 2as formula if you apply. See, while it is falling, so positive plus g you can take, initial velocity will be 0. So if you try to find out Vb is equal to under root of 2g into the distance from here to here. If it is x, if it is h and this is x, the remaining distance is h minus x. So velocity at B is equal to under root of 2g into h minus x. So kinetic energy at B is nothing but half mv square. V square means root get cancelled. So 2g into, so h minus x will come. 2g into h minus x will come. So if you simplify this, see, if you try to calculate potential energy and kinetic energy, sum of potential energy and kinetic energy at B. So 2 get cancelled, mgh will be there, minus mgx will be there, plus mgx minus mgx get cancelled. So total energy at A is mgh, total energy at B also mgh. So it does not change, the energy will be remains constant. Potential energy, of course, at A will be there, kinetic energy at A will be 0, but kinetic energy and potential energy are exist at the point B. So it means there is certain kinetic energy increases, potential energy decreases. So this is happening. So that is called law of conservation of energy. Law of conservation of energy, energy remains constant. Energy remains constant at any place. If you try to find out at C kinetic energy, see, potential energy at C will be 0 because it is there on the ground. On the ground there is no height. So mg into 0, 0. Kinetic energy at C, it is nothing but, if you try to calculate V value, the velocity at C is under root of 2g into the distance is travelled h. That's why kinetic energy at C half mv square, if you try to find out, half mv square, if you try to find out, the value is again sum of potential and kinetic energy at C is also mgh. So kinetic, see, sum of both energies at A is equal to sum of both energies at B. So mechanical energy, sum of both energies like kinetic and potential energy is nothing but mechanical energy. So that mechanical energy will be remains constant at any place in the, okay, so while freely falling body. Similarly, if a body projected upwards, that is also remains the same at any point. So the mechanical energy, sum of potential and kinetic energy remains same. So this is about law of conservation of energy. This is explains law of conservation of energy. If you try to calculate the value of kinetic energy and there is certain mass, height is given. So let us take the height value. So 200 meters if you take height, and the speed is equal to 10 meters per second. See, 10 meters per second, or you can take, okay, 200 meter height, mass is 5 kg, then speed is this much, kinetic energy will be. So if height, if it is given, automatically the remaining things are coming. 62.9 meters per second, the mass is 5 kgs. If you take, the kinetic energy will be 9800 joules. So these are the values. So if object is dropped from the height of 200 meters, the speed will be this much, and mass is, if it is 5 kg, if you change accordingly, the kinetic energy will be changed. We are ignoring the air friction, then only you are going to, since you know the velocity, mass and all these things, you can have the kinetic energy, and you can also have the force, how much force is applied. So this is another example. We will discuss more clearly in the next video. So thank you very much. Thank you for watching this video.